guys. It's that time. Welcome to the February meeting of the Forsyth Amateur Radio Club. We've got a lot going on this evening. Great program, thanks to Raymond. He's done something really cool for us, a digitized video that's going to be really enjoyable. A lot of other things that we need to cover as well. So we'll go ahead and start with the introductions. I'm Tim, AG4RZ, and we'll go around the room and let everybody get a chance to introduce themselves. And if it'd be a good time, if you've got anything that you're looking for, want to sell, want to buy, you can ask that as well.
Tim, KF4HHG.
Yeah, AL4XC, and if anybody can program an ICOM 706, then come out to my house.
I'm Van, KC4WSK.
John, M0KTY.
Tag, K4TAG.
Bob, I'm still studying.
George, KK4FA.
Bill, KF4MNB.
Jerry, WA4ZKI.
David, N5WND.
Woody, KF4PLQ.
Bill, W4EH.
Doc, WB4QIZ, and did anybody make any contacts on the DX position off the coast of South Africa? I mean South America last week? You did? Okay.
I can't remember what to call it.
Yeah,
HK0.
yeah, HK0.
Oh,
We
yeah.
did.
They're working on 8 bands.
Good, wow, I only got one. That's good, thank you.
Raymond, WX5 AAA.
K4DBS, David.
Barbara, N4BW.
Walter Klein, KI4XX.
David, KJ4OIL.
Jim, WA4NOT.
John, KJ4UFG.
Jared, K4GW.
Bruce, WB4QCM.
Bob, and I'm just starting.
Jim, AK4GAD.
Don, WS4NC. I have some newsletters here. My printer broke down, so I only got 15. And I would say there's like 12 left, so you're welcome to fight over them. Renewals will go out soon, I promise. I've been traveling a lot. You want to bring up field day later?
We can go ahead and do that now.
Okay. Gene, well, I'll tell you what, I'm gonna leave that to later and let you cover that.
All right.
I got some QSL cards here I thought I'd pass around. We're gonna file them in the club. There's one from Zach Reynolds. Everything he did was bigger than life. One from Charlie Everest, and one of our club QSL cards from December 28, 1930. Actually, I think this was mailed in the 50s. And one from Forrest Shelton, that when he was Piedmont's chief pilot when he retired, and he was a club member, and this was from Libya. And there's an article about him in the newsletter. So I'll pass those around. Is Jeff Stafford here? I have something to embarrass him with later. So,
Doug, KJ4IGQ.
Mike, KB4WJA.
KB4GKI. Jimmy.
I'm Eric, WK4CW.
All right, did we miss anybody?
Ben, K4GHS.
All right, with that out of the way, the next thing up on the agenda would be the minutes from the last meeting. Unless I hear a motion.
I make a motion that we accept the minutes as they've been written.
Actually, they're in the newsletter.
That's why they were written.
Yes, sir.
Second,
Second.
all in favor?
Aye.
All right. Treasury report, obviously Henry's not with us tonight. He's attending his daughter's birthday party, but he did leave a little information with us. We've got $2,006.27 in the account right now, so we're doing pretty good. There was a breakdown in the newsletter of the money that was made on the Ham Fest. We did really well with that. So all in all, we're sitting really nice to be this early in the year. We are looking at taking some of that money out, though. Dale has requested the funds for the repeater that have already been voted on and approved, and that's going to be in the neighborhood of $1,400. The good side of that is the fact that we're requesting the funds for the repeater, which means that obviously that'll be hopefully in our hands soon, be able to get in place. So as soon as he's done with testing, we'll get a full report from him. Let's see, and since Henry's not here, Dale's testing, that would leave Aries to Mr. Mansfield if he's willing to cover it.
Sure.
You slid away on me.
I'm hiding. Yeah, we're, got our first event for the year, Saturday, the Pilot Mountain Payback, half and full marathons. And if the 10-day forecast is right, and it's really gonna be in the mid-50s, that'll be okay for not only for the runners, but also for us working on it, since we're not gonna be running and breaking a sweat like they will be. Tim has done a set of full-color maps of the area for the folks that are gonna be working. And I'll get you one for that. Haven't had it yet. We've got people, some folks will be working a full day, otherwise part shifts, half days. Net control, Eric's gonna be starting net control from home. And then Jimmy Holbrook, KV4 GKI, is gonna pick it up from up on site, up at the, what the park calls the park office and what the race guys call a visitor center. I'll be at the start-finish line, and Jerry Brownlee's gonna cover that for the afternoon. We have two folks from the Surrey Club. This is in their territory, but they're having their Hamfest this Saturday. But two of their folks, Brian AB1JU and Michelle KB1UNY, are going to take the top of the mountain for that. It's kind of a 4-hour slot in the middle of the day, and then for the benefit of their club, they said that when they finish their shift, they'll come around the other air stations and photograph it to put in on their club website. So, you know, clean up a little so it look good for the pictures. Or else you can look, you know, really tough duty type stuff, mud up to here or something like that, whichever. John Kippy, and N0KTY, and David Ramsey, KJOIL, are going to be working the point at which the track crosses Stony Ridge Road. Tim's going to be taking the crossing at the Pinnacle Hotel Road, and we've got Stephen Myrish lined up for a sag wagon, or maybe a reassignment, because I'm still chasing down the race director to see if he really is going to have a wagon. They haven't done this before. They haven't used radios before, and they've never had a sag before, but they thought it was a good idea. So all in all, it looks like we're in a good position to help out an organization, a runners organization that we haven't helped before. This is new to them, so that's good PR for us. Dave Arndt and at least one of his assistant ECs from Surrey are going to be observing so that they can learn how to do it the way we do it, because they've got an event coming up later in the spring in Mount Airy, and want to be sure that, want to get some good ideas on how to run one, and you guys do it well. So they will get good ideas from this operation. And of course, it's good training for us. This is the first time we've done an extensive foot race. We used to do the St. Leo 5K, but they discovered cell phones, and so we haven't done that in a while. But that was city territory anyway. This is wild woods. These people are running cross country. Okay.
Let's see, a couple other things. Emails or written letters addressed to the club in regards to the shack equipment that the list was printed in this month's newsletter. If you've got any preference about what you'd like to see done with any of that equipment, let us know, either by email or by handwritten letter. There's a time period there that we're giving you to speak your mind about it, and then it's all going to the committee, and we're going to decide what we're going to do with the equipment, what's going to keep, what we're going to sell, that sort of good stuff. It is not a run on the club equipment, to reiterate that. Basically, we just want to update the shack. And last but not least, the Dobson Hamfest, formerly known as the Elkin Hamfest, is this weekend at the fire department in Dobson, just off 601. If you can't find that, then you're in real trouble. So, having said that, is there any new business? Okay. I do have one piece. Gene wasn't able to make it tonight. He's working. He has field day chairman has asked for volunteers for the field day committee for antenna work, site reconnaissance, and that sort of good stuff. So anybody that would be interested in helping him out with that, if you just, name, call sign, an email address or a phone number, somebody get in touch with you, he would be greatly appreciative. We're gonna try to get started on that early this year because we're gonna change things a little bit. So different antennas, different layout, obviously. We're going back to 100 watts, which is gonna be interesting. So anybody that's interested in playing, he'd be grateful for the help. So, with that, I guess we'll go ahead and start the program, and then when Dale, everybody gets in, we can do our update.
And he was licensed in this country in 1968. I think you emigrated about in the 50s.
Yeah.
And of course, those of you that are DXers, he was in Iran. He was EP2FR for a couple of years. Those of you who have been working on the radars in Iran, this man put them in. He's an advisory engineer and program manager of the Command and Control Division of Westinghouse right now. Within this month, end of this month, he will join the ranks of the retired. Frank Rudder's call is K3AW. That is his American call. When he was first licensed back in amateur radio, it was in England in 1938. He was a member of the Royal Air Force from 39 to 46. He was licensed as G2 FMF in England in 1946 to 53. And he was licensed in this country in 1968. I think you emigrated about in the 50s. Right?
Yeah.
And of course, those of you that are DXers, he was in Iran. He was EP2FR for a couple of years. Those of you who have been working on the radars in Iran, this is the man who put them in. He's an advisory engineer and program manager of the Command and Control Division of Westinghouse right now. Within this month, end of this month, he will join the ranks of the retired. I touched upon him being in radar and communication system, air defense, and air control. He is a registered professional engineer in the state of Maryland. I don't know about Florida. Are you going to hang out your shingle there?
I don't know. We'll see what happens.
All right, he's been a good friend and a very thoroughly competent antenna man. So, turn it over to you.
Thank you, Ralph. Well, I'm not sure I deserve all that fulsome praise, but very glad to be here and run this by you. The demonstration you're about to see was put together really for people who are not too crazy about meeting Maxwell's equations on page 2 of the antenna book and want to really use antennas without being particularly knowledgeable about why they work, but just how they work. And of course, a lot of people, once they get to know how they work, then get more curious and want to find out why they work. So we have been doing this now for about 7 or 8 years and found it to be a very, very big attraction for the ham clubs. And also, it is attracting attention now as a training aid possibility for even the military. where there's a resurgence of interest in HF, I guess because satellites have proven to be vulnerable, or thought to be vulnerable, and HF has some possibilities that other modes don't have, and so it's becoming attractive. But there's a whole generation of people sort of grown through now who've never used HF very much, possibly not in the Navy, but in the other services, and so there's a gap in the education. What we have here is a small ground plane. It's just an ordinary aluminum chassis. It's rather small for some of the experiments, as some of you will realize, but the name of the game was to make the whole thing portable so it could be packed in a suitcase and carried around easily. There is underneath there a small 10 centimeter, 3 gigahertz oscillator, which is chopped at 1,000 cycles, 50% duty, and then goes through an isolator to protect it from the atrocities I perpetrate on its load, and then through a directional coupler which allows me to measure to investigate the reflected power. I have here a double stub tuner which allows me to tune up the antenna system, and then I can select one of 3 ports. There's a coaxial screw fitting, OSM fitting, a balanced fitting here, and a single spike for vertical antennas there. So that's what we have. We have here just a crystal detector, and this drives into a small guitar amplifier down there to provide a tone. We've tried various methods of displaying this, but audibly seems to have worked out the best because people find it difficult to look at 2 things at one time. Anyway, we're looking at the reflected power from this antenna now, and I can tune it with the antenna coupler, antenna tuner, which is, it's analogous to a ham station which has an antenna tuner in the antenna circuit. The receiving antenna is just a simple 2-element Yagi type antenna with a balanced to unbalanced transformer on it. And this, of course, allows us to inspect the antenna. The antenna we have on here is probably one of the most commonplace antennas. It's a vertical quarter wave with a tilted ground plane. If it were folded right the way down, it would look like about a folded a sleeve dipole with about 70 ohms impedance, 75 ohms. If it were folded up, it would look like about 40 ohms. And so you bend it down somewhere in there, you can find 50 ohms, provided the other dimensions are right. And this antenna is radiates there, omnidirectional around in the azimuth plane, but polarized vertically. As you can see, there is such a thing as polarization. Polarization is defined usually as the direction of the electric field, and it's easy to remember on a dipole. Since the ends of the antenna don't go anywhere, there's no current can flow, so the voltage must appear there. And since the voltage is opposing each other at each end, you get an electric field between the two, and that's by definition, is the plane of polarization of an antenna by generally accepted convention. So this just demonstrates what you get. You see there's not much up here. That then defines what we have to work with here. And working on from there, we take a look at various different antennas in growing degrees of complexity. Probably the simplest antennas, and certainly the first, were vertical antennas. And I need this scale because these just look like bits of wire to you and to me until I find out how long they are. We have here a quarter wave vertical. It is held vertically, it could be a quarter wave horizontal, but and we plug it in there. It doesn't match quite the same as the other one did, but there we are. And now that vertical, now I put it in there for a reason you'll see in a moment, that as a performance which you're all familiar with, low angle radiator, omnidirectional pattern. Now then, that works fine provided you've got a backyard for hams that's aluminum covered, which is very rare. And simulated leather on aluminum is even rarer, of course. But that's what you get. Nice low-angle radiator, vertically polarized. And on the polarization issue, before we go any further, I want you to notice that the polarization is a very sharp, the cancel null is very sharp. So that you've got to be really cross-polarized to lose the signal to any great degree. It rapidly comes up. And in that respect, that's where I think some of these plans that the television stations are talking about radiating circularly polarized signals, that is to just give people who happen to be receiving a signal at some odd polarization where they are a chance to at least once a cycle to get a crack at the signal anyway. Moving on this thing, one of the things you have, of course, is a ground which is not perfect, not like this. And we have here a ground which is not perfect in more ways than one. This is a piece of lossy material. It's used in radomes in aircraft, as you've probably seen it. It's about 22 dB vertical incidence loss at 5 gigahertz. At my frequency of 3 gigahertz, it's about 8 to 10 dB, which is fine because I didn't really want a dead lossy earth, just a slightly lossy one. You can see it had an earthquake in it, but it works quite well nevertheless. Now, as we come along on this, there's your antenna. Now then, if we put a lossy ground down, see it's not nearly as good as it was. However, fortunately for us, there are things called radials. Now, the losses in the antenna break into two pieces. One is the series loss. An antenna is a two-terminal device, even a vertical unipole like that. The other terminal being the ground, or earth, or mother, or whichever you choose to call it. And that is a very elusive thing to get a hold of, except possibly in salt water. And so the resistive losses are quite variable depending on the ground and how you get hold of it. But they can be reduced somewhat by using radials, wires which stretch out from the base of the antenna. There is another loss, however, which is with vertically polarized antennas, is due to the dielectric and resistive losses in the actual medium there, which is very difficult to beat unless you're going to pave the whole countryside for miles with a reflecting layer, which is what happens in the ocean, of course, with salt water. So these antennas work very, very well on ships. Looking at this there, we should be able to see an improvement in signal. Not too evident. Yes, it is noticeable. Anyway, that does indicate that radials do pay off, and there's only half a dozen on here, but about 16 is where the curve begins to flatten. This ground effect, this ground pattern is particularly critical with vertically polarized signals. Vertically polarized antennas, and what happens is that instead of getting your nice low angle radiation, the bottom of the curve curls up, and so that as the lossier the ground is, the more it curls up, and you don't get the true low angle pattern you'd expect with a perfect earth, and which you get pretty nearly at sea with the salt water. Well, the vertical antennas, of course, quarter wave, people immediately would like to see things a little taller than that, because there's evidence that if you get higher you can see further. And so you can put in antennas of an increased height. Here's a half wave vertical. I think that's the right one. Oh no, that's not right. I beg your pardon. This is a half wave vertical. It has in general the same radiation pattern, but it's quite a different impedance. When you connect to an antenna, you see some kind of impedance. This is, if you have a resonant antenna and you correct to the current loop, you see a purely resistive load, and it's often referred to as radiation resistance. If you grab hold of it somewhere else, it will have some reactive components. It'll have an impedance which will change along the length of the antenna. But if you get one that is not resonant, it will have reactive components. But generally the radiation resistance is referred to with a resonant antenna structure. And this is a half wave, so it has voltage maxima at the ends and a current loop in the middle. So it is a high impedance feed point. This has advantages in our case because one of the losses we mentioned before was the ground resistive loss. And since you've now raised the feed point impedance of the antenna, the resistance loss in series with that hasn't changed, and the current in the circuit has gone down considerably because of the impedance it rise on the antenna. So it can be a more efficient way. The only trouble is that it's very hard to connect to it with that ubiquitous 50-ohm cable that everybody's hooked on these days. In the bad old days when people used open feed lines and so forth, it was very easy. But for some reason or another, well, I guess the reason is convenience. Everybody wants everything to look like 50 ohms now. Anyway, this gives you the same sort of pattern as the vertical quarter wave. And is quite an effective antenna. It's more often found in the slightly longer version, which is a 5/8. That's this one. This is about the longest antenna you can put up without getting into lobe structure in the vertical plane. A 5/8 wave antenna is very common in the amateur fraternity. It happens to have about 185 ohms of capacitive reactance. And if you put a coil in to cancel that, you finish up with almost a 50 ohm feed point impedance at the bottom, which makes it a very convenient thing. It has a good pattern structure, a little more gain than the quarter wave. You can, of course, go even higher, and this is a 3/4 wave antenna, which would have a fairly low feed point impedance, but it's starting to show, see, it's not as good down there. Now you've got the lobe structures appearing. So you've gone from 5/8 to 3/4, and you've lost a lot of your lower coverage, and it's now coming up here. So one of the ways, of course, to make the antenna taller and radiate still in the low angle radiation is to try and get the phasing along the antenna to be all the elements of the antenna in phase. If you just make it longer, of course, it changes. But one of the ways to make it in phase is to, after half a wavelength, you fool Mother Nature by tucking in an odd half wavelength and then slipping another one in here, and those two are now in phase, we hope. And now, real good low angle radiator. That is appears in the trade, not quite like this, but similar, a Ringo Ranger, which is, they use 2 5/8 wavelengths with an 1/8 wave stub. It's a kind of extended double ZEP, as the old timers will remember. Of course, years gone by, a gentleman called Franklin tried this game, and he made these antennas. The only trouble with Franklin antennas is they've got all kinds of gain, but practically no bandwidth. So this one's not a very good one. They're very difficult to make. You see, you feed them from the end, and it means you've got to get all the phasing absolutely right. Otherwise, you don't get them to operate properly. But they can be made quite effectively. Probably the vertical antenna carried to absurdity is this one here. That's an 8-element collinear stack, which appears, not the 8-element version, but the collinear stack appears in many commercial antenna installations, and I believe the so-called station master antennas and such like. But what you have here is a series of half-wave elements. That's half-wave in the cable, not half-wave in space. And they're just crisscrossed inner to outer in a coaxial cable. And you get a result. See, there's very little activity down there. But of course, if you live underneath this antenna, you don't hear much. But if you move out a little ways, these are very effective. And by altering the phasing, you can make that thing bend down or go up. And quite often in the commercial applications of it, they do tilt it down a little bit. Of course, it's an end-fed antenna, so you don't have even current distribution all along it. But it does work fairly well, as you can see. Very narrow horizontal beam out of that. Of course, it's still vertically polarized. The next type of antenna, which appears frequently, is the dipole type of antenna, and they have been a good old standby for many years and still are. One of the facts that emerges at this point is that in order to work with antennas or talk about antennas, you can't talk about frequency or dimensions in feet and inches. You have to talk about it in wavelengths. It's the relationship of the various parts of an antenna in wavelengths that determines how it behaves. Here we have an antenna which is a half-wave dipole, a quarter wavelength high above the ground. And that's when we plug it in, it is. So that has a characteristic pattern which makes it very useful for some things. When you, as often happens, people come and ask me and say, well, what sort of antenna should I put up? And I wait for them to finish the question, but they never do, you see. And then I have to ask a series of questions in response, which is, well, what do you want to do with it? If you want to just keep in touch with your brother in New York, it's one thing. If you want to work the ends of the earth, it's another. And if you want to be a real big noise at the ends of the earth, it's something else again. Or if you just want to work 2-meter repeaters, it's a very simple problem. So this dipoles provide an interesting illustration of the sort of things that happen with the same antenna essentially, but put up in a different way. And this is what baffles a lot of people, is that they apparently put up the same antenna as someone else did, but it doesn't behave quite the same. So here we have a half-wave dipole, quarter wavelength high. It has a very definite pattern. Doesn't have much low-angle radiation. It's all up here. Horizontally polarized, of course. And, of course, if you look at it, that antenna has a lot of usefulness. It's very very useful for short-haul communications from 20 miles out to about 400, 500, 600 miles. It's also very useful if you're parked in a valley and you have to get over the mountains to get out of there. It has been known to work long distances on multiple hop, but it's predominantly a medium-range antenna. And one of the problems the military have is that they like to just stick up a whip antenna and work with that. But a whip antenna is not the right antenna for medium-range operation. If you look at the propagation characteristics on the position of the layers, you will see that in order to work out to about 400 or 500 miles, you've got to have radiation above 45 degrees. It's got to go up and then down again. Most verticals near the ground petering out before they get to 45 degrees, so they're low-angle radiators. So they don't do very well. In fact, in some experiments I ran recently, we showed 26 dB difference between a vertical whip and a horizontal dipole, a dipole which I could touch, incidentally, with my hand anywhere along its length, versus a whip on the roof of a shelter. Now, there's an interesting thing about this dipole. Most people regard a dipole, per the textbooks, as having a sort of figure-of-8 radiation. A low dipole is essentially an omnidirectional antenna. Here we have a helical antenna, which is not sensitive to polarization. It's a so-called circularly polarized antenna. Of course, everybody knows that there's no such thing as circular polarization. It's just a rotating plane wave. So here we see it doesn't care. But look at this. The angles at which that antenna radiates, it's omnidirectional, in which you can use it. So you don't need to fuss about the polarization. Now, if you're worried about off the side, as we will do with some of these higher dipoles, that other factors enter it. But a low dipole is a medium-range omnidirectional antenna, and a very effective one at that. So we'll move on from there. The next thing to do with a dipole, of course, is to crank it up higher in the air and see what happens then. So we go up and we move that thing up to half a wavelength. We find it makes quite a difference. Here's a half-wave antenna. You'll find that we have a radiation angle is much lower. And the vertical stuff has almost disappeared. In fact, if that antenna was exactly at the right height, it would have disappeared. So now you've got, now it's behaving more like the textbook dipole. It still has this stuff up here, high angle, vertical, looks like vertical polarization. One thing to remember, though, is that with this polarization thing, people get very hooked up on it. It matters probably line of sight. But once the energy is bounced off or been refracted by one of the layers, all the polarization bets are off. It's just circularly polarized or scrambled, and it doesn't really make much difference. Provided you've got an antenna that will collect the energy from the direction in which it's coming, it will work no matter which kind of polarization you've got. This is not always true with line of sight, where you've got a clear, no Fresnel interruption and so forth. But for HF work, that is, using reflecting layers, then either polarization will do just as well. There are advantages to circular polarization, but not in the generally accepted sense. They only enable you to get a better crack at randomly polarized signals. Now, this antenna, of course, is a better antenna for longer distance, yet it will still provide you with a certain amount of high angle coverage. So it's a transitional antenna from medium range out to a little further out. And you can haul it up and down and make it do these things for you. Of course, if you've been following what we've been saying, you'll find that we raised the antenna and the radiation angle came down. So if you're interested in long distance communication, then obviously heading in that direction is what we need to do. So we'll put it up to 3/4 or so of a wavelength. I think that's 3/4. And we should get an even lower angle of radiation. We do. A no, and then that stuff up vertically is back again. And if you put the antenna one wavelength high, just to confirm what's going on, now you've got a really low angle. You'll realize, of course, the purists in the group, that once I start getting the antennas up here, that the ground plane is getting rather small for the experiment. It should be extended further, but I can't get it in my suitcase, so this is the way it is. Now you see you've got a nice low angle. There's your null. High angle, and then another null, not quite so clear at the top. So now you've achieved some much lower angle radiation, but of course you've lost some of your benefits by you now spraying a lot of it up in the air. These antennas, the horizontally polarized antennas, are much more predictable, and the ground behaves much more stably as a reflector than with the vertically polarized antennas. It just hits the ground, suffers a phase, or enjoys a phase reversal, and then comes off again. Well, now you've achieved this low angle radiation, but you're now spraying stuff upwards. You would like to stop that. So the way to stop that is to stack two of these things. You've got the one at a wavelength high and one now half a wavelength below it. And you'll find that this produces a desired effect. Low angle radiation and no stuff up there. That's where the W4s down in the Carolinas, they seem to grow these things down there. However, there may be an occasion when you would like still to talk to your friends locally. So if you've got provision for switching the feeders to those two antennas, you've got a reduced low angle, and the stuff is up there again now. So you can, by throwing a switch, either have low angle or high angle on these antennas. Of course, they do get a little big at the lower frequencies, but there's all kinds of old sayings like you can't make an omelette without breaking eggs, and so on and so forth. There are some antennas that are derivatives of the dipole called the inverted V. These are for people who are too cheap to put up two supports or have just one support and want to make the most use of it. An inverted V is a quarter wave high at the center. It has a somewhat different characteristics than the quarter wave high ordinary dipole. It has, of course, the high angle radiation off there, but it has produced off the ends now some low angle vertically polarized stuff, which was not there with its predecessor. Here's the, you see there's very little down there. You're now getting into the overall pattern up there, but we put the inverted V back. For those in the back, these two antennas have just happened to come out orthogonal to each other, but doesn't spoil the experiment. See, you've now considerable radiation low off the end. No, I think there's more horizontal up at the high angle than there is vertical down here. A little bit. But it's putting some stuff down there that wasn't there before. And it's a useful antenna. If you hoist it up a little higher in the air. Of course, these antennas have no ground terminal losses, but on the other hand, they still have the reflection absorptive losses. You still got that. I think there's more horizontally polarized stuff, but there is some signal coming off there now. And if anyone sat and listened to signals coming from a distance and watched the signal strength meter on the radio bouncing around by 10 or 15 dB, you begin to realize that the 3 or 4 dB difference between those doesn't really amount to much until signals start to get down in the noise level. For the people who like to do things differently, there's the V. It's similar. It has a dipole type of response. It has low angle radiation with one difference: a null off the end. So if you can figure out where you don't want to listen to and tilt that antenna, you can do it. So generally that gives you a quick rundown on dipoles. But as you can see, there's a considerable amount of flexibility available in relatively simple antennas, things you can put up in the average backyard, or which another area is which the tactical military people can string up in places where they are just arriving in a hurry and possibly leaving in an even greater hurry. Having got through the dipole bit, there is something you can do with dipoles, and we'll be quite brief on this. Obviously I can't change the frequency on this, but I can change the size of the antenna relative to the frequency. It's strange, you know, that some of these things that even people in the business have, they realize after you tell them that this thing happens, but they'd never thought about it before and realized that it happened. You can use a single dipole antenna at harmonic frequencies, or at any frequency, if you provided you tune up the system. You'll notice I'm using open wire feed lines on here, and they're about 130 ohms. I make it myself, and you can resonate the whole system. As an almost lost art in antennas these days, but very useful if you're, as many hams are, in a position where your antenna options are very limited. But if you can resonate your feed line, and by using open wire feed line the losses are minimized compared with coaxial cable, you can use antennas on many different frequencies.
With high VSWR.
Well, there's high VSWR on the feed line, since it's now part of the whole resonant system, but since the feed line is so low loss, it's air most of the way, it doesn't contribute much in the way of losses, and since it's a balanced system, and if you do it right and keep it small dimensions relative to a wavelength, it doesn't radiate very much, so that you have a fairly efficient system. I'll just take one example of this. If we want to use that dipole we saw before on the third harmonic, that's the dipole on its basic frequency. That's on the third harmonic. It's now 3 quarter wave each side, or 3 half waves in total length. And one would say, well, that's now a bigger antenna, it should be better. And it is, but it acquires some other strange habits in the process. That antenna now is, see, it's fairly miserable. It doesn't do much at all until you come around here. It's now high, you see, so it has a lower angle of radiation. It has a minor lobe and 4 major lobes, and 2 major lobes each side. And that's a characteristic of antennas, that when you make them longer, they develop a series of lobes. Every half wave longer, it develops another pair of lobes. So if you're a ham, of course, this provides you access to other people that you didn't have access to before, that you now squirt in a different direction. However, one of our German friends has come up with an antenna Not from Texas. No, this is from Germany. One of the things, as we discussed briefly, in vertical antennas, if you can maintain phase coherence along the length of the antenna, you can make it just have one lobe and radiate one direction. Now this antenna is 3 half waves, and the design arose from some computer studies of the radiation patterns of random wire shapes. And I'm not sure this antenna is optimized. I only got the information the other day, and I just bent it up as best I could to the way his instructions said. This was published in the 1978 Antennas and Propagation Proceedings of the British Institute of Radio Engineers. However, the paper came from the University of Munich. What they've done here is you've got a central half wave which radiates, of course, and at some point in space it has a certain phase vector. Now, by bending these around, the energy arrives down here a little later, and it catches up, if you like, speaking in simple terms, out in space, and you wind up with 3 half waves in phase, if you do it right. And this can be expanded into a Yagi type configuration, 3-element, with, they claim, up to 17 dB a gain out of a 3-element antenna, which is kind of big at ordinary frequency, but the VHF gang would probably have a lot of fun with this one. See? It's a little bit off the side. I guess that's coming off here. I'm not sure this is optimum. But you see the side lobes have now disappeared, and all the energy is now traveling. It should be direction in that direction. I've obviously not got it quite right yet, since there's still some energy coming off the back. But it is directional to some extent.
What is the name of it again?
I don't think it has a name. It's just... well, that way. Anyway, this is a new one I only found a few days ago, and I haven't really researched it, but I thought you might be interested in the possibilities of something like that. The most popular gain antenna is, of course, the Yagi, or derivations thereof. Gain, of course, for those who are not too bored to listen, is not something that's manufactured. Gain is where you find it, and that's not always where you expect it. The definition of gain is basically with reference to an isotropic antenna, which is a point source radiating equally in all directions, which of course is not often found in nature. So the normal reference is a dipole, which has the familiar free space dipole. Of course, free space would be nice if you could get out there, but we have to live in half space, so that modifies it. But a free space dipole has a gain of about 2.15 dB over an isotropic. That gain being derived by the energy off the ends is no longer radiated. It's all concentrated in that donut around the antenna. And that has gain, how gain comes about, because you've taken energy from one place and put it someplace else. And pursuing that still further, you can do that by a number of different ways. The Yagi is a phenomenally successful antenna. In fact, it's one of the few attempts that almost manages to fool Mother Nature. When you consider that antenna has almost as much gain as that antenna, or that antenna, or that antenna, you'll see that it's a particularly effective little thing. Now, it doesn't have the bandwidth and several other attributes of these other antennas, but there's no such thing as a free lunch. You know, you have to give up something. In the early days of the Yagi, the folded dipole became very popular. When you folded dipole, you cut it in half, the current in half, and the impedance goes up 4:1. And you say, well, what good is that? Well, it's good because when you start adding other elements to it, which are like coupled circuits to it, you drive that impedance down again. And if you started with a 75 ohm impedance to begin with and drove it down, it's hard to cope with, but if you crank it up to 400 or 300 ohms and then start driving it down, you can get it back to where you started from, and this makes everybody happy. Of course, nowadays with these type of antennas, we've gone away from the folded dipole more to gamma matches and other types of matching systems, resonant matching systems. The folded dipole behaves exactly like a regular dipole at half a wavelength above ground. It's same as we saw before. Now then, if you add a reflector to it, and this reflector is what the experts have determined is optimum spacing, 0.15 wavelengths. Of course, now if you want energy to go back to the reflector and then travel this direction, you're not in the right distance spacing for that to happen. So you have to introduce some phase shift, and that is done by making the reflector inductive. And this then ensures that the energy coming back from there, having been delayed, then arrives in phase to travel in that direction. So we have here a radiator and a reflector, which is the same thing that I've got here. Now you see that behaves much like the dipole, except much of the energy is now cancelled out in this direction. It's all travelling that way. Well, if you can do that with a director, you can also do it with a director. And it's been determined that about 1/10 of a wavelength is the optimum for this exercise, and it is made a little shorter. And in fact, this particular combination, if you can only put up 2 elements, is more effective than a reflector and radiator. You can get more gain out of it. And an excellent back-to-front ratio, believe it or not. Of course, flushed with success, you then marry these two together, and here comes the familiar 3-element Yagi, which is one of the most popular antennas in the world. And of course, if you want to be extravagant, you can add a board of directors, and you now have an even lower angle of radiation, narrow beam, most of the energy headed that way. Of course you can play tricks with it, you can do this. Another antenna that has attracted attention is the so-called quad, reputedly have been developed in Ecuador when, with 50 kilowatts, the Yagi coroned off the tips and melted. So they bent the ends down, joined them together, and with 2 stacked Yagis, and came up with this. This antenna, incidentally, I made entirely cookbook from the ARRL antenna handbook. Strictly, I didn't make any trimming on it at all. It's a plumber's delight quad.
How about the vertical radiation? Right out front. Well, that's what's that theory.
That theory never really did exist. Though you can read books written by otherwise eminent men who state that the reason for using A quad is that it radiates both planes of polarization. Not so. Not unless you did it. No, sir.
You can jump that 45 degrees?
I happen to have. What would you score that for that one? I know, but that is all these are one wavelength loops. But what would you expect the plane of polarization of that is based on your diamond theory?
It's going to be plane
Which direction?
follow the electric vector.
Now, come on. Horizontal or vertical?
That one right there?
Yeah. And we happen to have a diamond here too. Or even
Well, you'd have to feed it on the corner.
even a delta loop. Whichever way, the plane of the polarization on any one wavelength loop is across the direction of the feed point. Well, we could make it. Doesn't the shape doesn't matter as long as you enclose a reasonable area with the antenna. And there are some claim there are some special shapes like this that work, but I've not been able to make that one do any better than anything else. One thing you can do. Somebody says, well, you know, if we vertically polarize the antenna, it should give us low-angle radiation. However, it turns out that it does, but it behaves just like a single vertical. It loses its directivity. Which is what you'd expect when you think about it. However, you can beat that one, but what happened to that particular antenna? Oh, here we are, it's in here. If you make two of those, you can get it back again. Of course, it's a little large on 80 meters, but... Yeah. There. Now then, of course, if you hoist it up in the air, if you want to prove your diamond, you can vertical. Now, if you want to really get fussy, let's just put one up at an angle. See what happens. Has a null right angles to the feed point axis. But it again has tended to get omnidirectional.
What happens to your Yagis as you raise them in the air?
The Yagis as raised in the air behave exactly the same as do a dipole. And in fact, they develop the lobes and so on and so forth. And then you have to stack them to get rid of the lobes. Both the quad and the Yagi behave identically with the dipole. In fact, all they are dipoles augmented. And so they behave, anything a dipole would do at that height, the Yagi will do.
So if I put in your TV antenna on your roof, is the wrong way to get? You've nullified the transmitter.
Well, it's possible to find a height where you will not receive a signal from one of the transmitters. Yes, quite often, particularly you can lower it a few inches and you can pick up the signal. It doesn't necessarily guarantee you to be at the right height. This is a dual delta driven loop, which is a very good way to go if you can. It's an end-fire array. An end-fire arrays, well, they have more gain than the broadside fire arrays. Do have one problem, that you've got to get the phasing, the spacing, and the power division right. So they become rather difficult to build and to make it work over a wide band without taking some special precautions. since the tuning of the loops themselves has a considerable effect on the directivity. This one, I guess it must shoot the other way. You never can tell. Every time I do this, I screw that one up. But they are some of the gain antennas. Now, of course, in recent years, there's been a resurgent interest in things called log periodics because they show a reasonable match and some gain over considerable bandwidth. And there's been an interest developed in them in the ham fraternity with the possible advent of some new bands. They are very good antennas for various reasons. As I said, they doesn't have any more gain than this thing, probably. Maybe a dB at the most. But for an 18-foot boom with one of these, you need 51 feet with a log periodic. I'm assuming this is a tri-band type coil-loaded beam. So, but they have some other attributes. This is a very, very clean antenna. However, the reason they don't perform according to their size is because at any given time, only a part of that antenna is doing any work. You launch the signal from the pointy end, and it goes down the transmission line until it finds something that looks like a reasonable radiator and starts to go to work. If we pursue this with a small capacitive probe, you find that there's So there's a peak in this region, which, interestingly enough, is about the same size as a Yagi. So what happens is the phase front runs up and down this antenna and uses 3 or 4 of the elements as a directional array. But it does have a lot of bandwidth. This one has got a 2-to-1 bandwidth centered on the frequency I'm using here. Well, the antennas we've been looking at, of course, are for fairly high frequencies when you consider that at 14 megacycles, which is a ham frequency, half a wavelength is 33 feet. It's not impossible to swing this kind of length of antenna round, and lots of people do it. Even in the Yagi form with several other elements. It's a fairly small turning circle. However, as you come to lower frequencies, you find that the antennas get very large. And also, the height of the antenna in wavelengths tends to get less and less and less. So you now face at the lower frequencies, if you want to work any appreciable distance, with trying to get some low-angle radiation out of the antenna, out of an antenna which is too low to the ground and very big. So you have to resort to, you can use verticals, of course, but they get pretty high. However, if you could put a dipole up for the frequency, there are some antennas you can use which play games. Here's, where are we? Here's an antenna. This antenna is a half square. It's fed at the corner. That I invented that way of feeding it. Usually it's fed at the bottom. But it looks like about 75 ohms in the middle. It looks like a dipole. It sees a quarter wave, half wave, and then another quarter wave. So essentially it's looking at the center of a dipole. The current cancels in this top section, so there's no horizontal radiation at all. And it just radiates as 2 vertically polarized quarter waves with no ground return, no ground path. Why don't you try to hit about 150? Okay. There's no ground resistance losses on this. Of course, the ground absorptive losses. But this antenna is no bigger than a dipole. And just with 2 quarter wave droops on the end. These antennas, of course, are not quite as spectacular as the Yagis and things because the gain is not as great, but they do punch the energy where you want it to go. And since this antenna has the current maxima, where the action is, of course, in an antenna, at the top, it's effectively higher than it looks. It's a very effective antenna. It's an antenna which is predominantly horizontal, but does not radiate any horizontal polarization. But it does radiate bidirectional. So there you have a low antenna with no ground loss connection and low angle radiation and no bigger than a dipole. And a dipole at that height, as you saw, blows most of the energy straight up in the air. So that's worth playing with. Of course, you can get clever with these things and put two of those. Now this is the more conventional way of driving these things, which is to feed them at the bottom. Of course you can put another arm on this side too, if you've got the room. But this one then becomes now, and if you run two feed lines to that and can switch them, of course you can make it go both ways. So there's a very useful antenna for those people who can't get up very big antennas. This is a bobtail beam, this particular type. Half of it is a half square, half of a bi-square. Bi-square antenna for the old timers was the full square. Another thing you can do, if you've got a tower which is holding up a rotary beam, you can hang a sloping dipole from it, since the hypotenuse of a triangle is usually bigger than either of the other two sides, and you get the usual sort of horizontally polarized stuff, but you get a significant low angle radiation. Now if you have a tower, there's a little bit. If you have a tower, of course, this has got guys on because otherwise it would fall over, and you put it just behind there, you'll find that
Did you resonate that?
a little bit. Now this accounts for the high degree of variability on these antennas. You see, what you have here is a two-element array, driven element and a reflector. And as we pointed out before, that with reflectors that are not perfectly spaced, then the tuning of the reflector is important. And so that you're using your tower and whatever's hanging on it as a reflector. And with this is a typical 50-foot installation. And you may find that where you put that with respect to the antenna within a few feet makes a tremendous difference as to how well it works. So if you're having difficulty getting directivity, run it up and down the holly a little bit and see if you can move it in and out from the tower, and then tune up your two-element array.
They say that 28 degrees is the magic answer.
28 degrees? Why?
I'm sorry. 28, yeah. So that doesn't work at 26, it doesn't work at 30, it's great at 28.
Empirical, I'm sure.
From your country.
That's 45 degrees. I can't intuitively see any reason why they have such a magic number. Now, if you were using long wire, long antennas and things, I can see reasons for that. Because as you get several wavelengths long, of course, around about 23 degrees is where the main lobe sort of comes to a rest when you make a long wire. No, I haven't seen that one. I don't know why it should be. we really need to know what the other parameters are. You know, it may be 23 degrees hanging from his gutter down to the cherry tree with the feeder wrapped around the house, you know, that kind of thing, and which is a kind of special case. Anyway, that type of antenna is very useful. And then, of course, there is probably one of the simpler antennas, the inverted L, and those develop more and more lobes as they get longer. You start with the smallest possible inverted L. It's just a quarter wave long and a quarter wave high. It's a fairly high impedance feed since it's a half wave antenna, so the ground resistance losses are not too great. The only trouble is with some of these antennas, you're liable to wind up with a lot of RF down near the transmitter and your operating position, so they can be a problem. I'm talking as to hams now, but of course the rest of the professionals can convert this into their own particular environment. It's got a certain vertical and horizontal, so it sprays stuff in every direction. It's almost a half-space isotropic antenna. As you lengthen it, it still does somewhat similar. It is somewhat directive, as like a dipole. As you raise it up higher, of course it still has a vertical component, but the null appears higher up and the angle comes down. If you make it longer, of course, it still retains the vertical, but now starts to develop lobe structure. The patterns shown for these antennas usually show a symmetrical sort of lobe structure, but it's not really symmetrical because the lobes pointing this way are due to the energy traveling that way on the antenna. The energy which does not get radiated then starts traveling back and produces lobes in the rear direction. And if the antenna is radiating anything very much, it's quite obvious that these aren't going to be as big as the others. And if you terminate this down to ground, then there's nothing coming back the other way, so you'll have a unidirectional antenna. But you do get see, the main lobe does tend to move closer to the wire as the antenna gets longer. And it sort of runs out of gas around 20 degrees. Still vertical. Now there's the reverse main lobe. See, those are the if you put up something like this, which is fed with a balanced feed, so you don't get vertical radiation, it's sometimes easier to see what happens. See, there's very little vertical off this one. Let's tune the antenna up. See the lobe structure there? You can notice it's greater this direction than that. This is just 3 half waves. The use of this, of course, is made in a V-beam and rhombi.
All right, that was interesting. Hope you guys enjoyed that. Sorry that it ran a little bit long, but I think it was worth it. Lots of good information there if you like to play with antennas. So. And with that, since it's 9 o'clock, are there any motions?
I'll make a motion that we adjourn.
Second. All in favor?